Good morning, everyone. In the previous sessions, we have learned how to process seismic data in sequence from stacking to migration. And today, we'll revisit this conventional procedure and find out the limitations. Based on that, we will introduce the new procedure, which is a pre-stack migration. For this session, I divided the material into 4 parts. So first of all, I introduce the concept of a pre-stack migration. And then we focus on the depth migration, as we mentioned in the pre-stack and the post-stack migration in the previous session. We actually said that ideally, the image of migration should be in the depth domain, but because of the velocity accuracy, because we don't have an accurate velocity model, so we intended to image in the seismic profile in the time domain. But we try to, in this session, we try to get the ultimate good quality imaging, so we want eventually get everything in the depth domain. Then we review the migration methods, which is basically compare the difference of migrations in the post-stack domain and the pre-stack domain. Finally, we will discuss one of the key parameters in the migration, which is velocity. So pre-stack migration methods. We learned the stacking based on the NMO equation. So this is a typical NMO equation, which only has 2 terms. But because of a Taylor expansion, in fact, we can have a higher orders, right? So for the ideal limit the source receiver offset, which means a small source receiver offset, we can use this formula to do an MO, right? So this equation is called the hyperbolic equation because all the 3 terms are squared, and on the right-hand side, these 2 terms are both are positive. That's the hyperbolic equation. Right. I emphasize this because we learned last week for migration, we have a similar, actually identical equation, right? I say similar because the variable here is offset, but that will be slightly different. That's one thing. Because both migration and NMO use the same form of equations, right? Same form of hyperbolic equation. So that means for post-stack migration, we can use the velocity derived from NMO for migration, right? There's a logical here, yeah? However, NMO only assume the subsurface is a flat layer, right? Not only the source receiver offset is small, but also the subsurface layer is a flat layer. But in practice, very likely subsurface has a dipping angle, right? let's see, that's a very straightforward mathematical derivation. If we consider this dipping angle theta here, now if we work out, you try to work out the travel time from S to here, reflection point, and back to the surface, the travel time will follow this formula. T squared equal T naught squared. T naught squared means the travel time at the midpoint, two-way travel time at midpoint, and this dashed curve, a dashed line perpendicular to the refractor, right? However, here, this term, instead of a 4h squared divided by v squared, now we have a cosine squared on top here, right? So if you move cosine squared to the denominator, your velocity will change from a v to v divided by cosine theta. You see that? So that means for the dipping angle, for the dipping layer here, the actual velocity is larger, right? Because v divided by cosine theta is equal or smaller than theta, smaller than 1, equal or smaller than 1, right? So v divided by something equal to 1 or smaller than 1, so the effective v here is larger, right? So that means the velocity we got from NMO is too small, right? If velocity is small in the migration, what happens? Velocity too low, the migration will be, come on, it's over migrated or under migrated. It's over migrated, right? Because this value here is smaller. That will be over migrated. That was one problem, the dipping. NMO didn't concede the dipping angle, right? Another issue, very likely, subsurface model is not like a single flat layer, but you could have both a flat layer here, but also a dipping layer for this CMP gather, right? So you have two arrivals in your CMP gather. It looks like this. Now, if we use this based on the dipping angle, you will have one flat, but another one overcracked, right? So that's difficult to handle simultaneously this layer and this layer. That's the trouble, okay? So this just tells us if we use NMO under migration, the result is not the ideal result, right? That's the problem. Let's summarize the problem for the sequential processing, stack plus migration. First of all, refractor not necessarily be horizontal flat, right? And the data is non-zero offset is not the image of subsurface. We do the NMO, but even after NMO, the NMO character trace is not necessarily equal to the zero offset trace. So that means the image is not a subsurface, but the image of Earth, right? Not the image of subsurface Earth. And the stacking will not give us zero offset data. Very importantly, as I said, you should distinguish data space and the model space. Here, your seismic data is in the data space, so that's the reflections. This is reflection or reflections, but they are not the model reflectors. Okay. So for these problems, what do we do? The solution here is called a Prestack migration. So we do not separate the develop processing into sequential steps with stacking and the post-stack migration, but we should do in one go Prestack migration. This is the concept. How to do the Prestack migration? Right. This is a seismic data. Horizontal distance x, vertical axis is t. So that's in the Prestack domain. This could be a short getter, could be a receiver getter, could be all common offset getter. Doesn't matter. Let's talk about a single sample here, single data set, right? So this single data set, I think single data sample, this is in the data space. This could be a reflection from this sort of curve, right? Any point, right? So this will be represented here. So we're talking about if source receiver on that profile, source receiver offset is constant. We call it constant offset profile. If this constant offset, I mean this midpoint source here receiver. If for this midpoint source here receiver here, right? So for common offset section, that sample can be from anywhere along this curve, right? So you have source, receiver, offset. We call H here. That's the midpoint X. So you can do the simple derivation. Your travel time is distance from here going down, come back, right? From a source part, you have a z squared plus x minus h squared, and then for the receiver leg, you have this form. So this gives us a so-called double square root formula, right? Double square root formula. Okay, let's see that if S and R gradually move to the middle point, which means zero offset, right? Zero offset migration we learned in the previous session, which is post-stack migration, right? Okay, if S and H move to M, so H is zero. H0 means here z squared plus x squared, right? Z squared plus x squared is there. And then here you double, you have 2 here. So this is exactly the zero offset migration formula, right? But now in the Prestack, which means your source receiver are not at the same position, there is offset h here. This travel time becomes this formula. It's called a double square root, right? You have one square root, another square root. You have a double square root means you have this equation. It means you have one we call the principal axis, major axis, another minor axis. So this is a elliptic equation. Okay, but semi means we only have a subsurface part, right? So elliptic equation. If you can remember what we learned for this situation in for the Prestack migration. For the Prestack migration, this circle is a perfect circle, right? Or the ellipse, because h equals 0 is a perfect circle. In the Prestack, the perfect circle becomes the elliptic curve. Okay, so that really means this point, this data sample could be a reflection from this point, or from this point, right? Okay, so what do we do migration? Basically, what do? We just spread this sample into the model space following this elliptic curve. It's straightforward, isn't it? That was for 2D case, but in fact, subsurface structure is very complicated. At least you do have a 3D effects. So for the subsurface plan look like this, you have an angle, not only the dipping angle, but also have a azimuthal attribution, right? So because 360 degrees. So the velocity here, instead of v square, but now it's v square divided by 1 minus sine square cosine theta. Sine theta square cosine phi, right? So again, if phi equals 0, phi equals 0 means that azimuthal is 0. So your dipping is exactly along the line, right? There's no any azimuthal factor. So this becomes 0. Cosine 0 is 1, right? And the 1 minus sine theta square is equal to cosine theta square, right? So this becomes exactly the 2D case, right? If theta is 0, cosine theta is 1, so that becomes exactly the ideal case, an MO case. Okay, so for the exploration seismology, we always do that way. For any methodology, the development always follow that way. You use the ideal situation and use a simplified model, and gradually, when you technology advance, they gradually will relax these assumptions, gradually consider more complicated cases. So now you can see the logical, you can see the relationship in here. So in fact, subsurface, when subsurface dipping layers here, your chop time actually follow this formula. So velocity, nevertheless, the velocity is smaller than the NMO velocity, right? NMO velocity was v, but here for the migration, the velocity will be v divided by 1 minus sine theta square cosine phi square. Okay. I mean, probably some students feel difficult to derive this formula. Doesn't matter, but if you use the same manner as I just used to simplify this to the 2D case and then to the flat subsurface interface, you can check formula. Okay, that would be help you to memorize that. So the problem really is 3D. In the 3D case, the subsurface reflector not only has a dipping angle, but also azimuthal dependent. Azimuthal means your angle in the horizontal plane, right? So again, your seismic data is not zero offset. You always have a non-zero offset. An stack does not generate a zero offset data. We know that because either subsurface is not the flat or the source receive offset is not that smaller enough, right? And also the layered structure, if you remember that when you layer structure, IMS velocity, which is mathematically derived, is not equal to the stacking velocity, right? And the velocity depends on dip, and as most of dependency on dip is cosine theta square, right? Which is equal to 1 minus sine theta square. And the dependence on the azimuth also cosine square. So it's a cosine square phi. Cosine square theta, cosine square phi, right? But mathematically it's a 1 minus sine theta squared and the cosine phi squared. Again, reflection, that's in the data space. It's not the reflector in the model space. With geologically, we're on the subsurface image, which is a model, right? So the solution here is Prestack migration. For 3D, how we derive a 3D migration formula. In the 2D, we will see that's very straightforward. So simple, a single sample is spread along elliptical curve, right? Just spread out. And then you do the all data samples one by one. You can do the trace by trace, right? But within trace, you do one by one. And then finally sum them together. That's the one way to the migration. For 3D case, they're almost identical, but the formula here is slightly different because you do have offset not only in X direction, but have offset in the Y direction, right? Because it's 3D. It's not that complicated, right? Just simple extension. Nevertheless, this formula is still a double square root. Okay, so this is still a double square root. Then this shape here is called a ellipsoid, right? Instead of a elliptic curve, but it's a 3D shape. So it's a ellipsoid. That's the migration principle. So that means if you take one sample from your 3D, in this case it's called a constant offset cube. Constant means your hx in the x direction same value, and the y direction same another constant. So for the constant cube, you just take one sample and spread the sample to everywhere, and you do all of them together based on the linearity. We just simply stack them together, right? That's called superposition. So that's the principle of data processing. So far, we just do see why we need Prestack migration, and also we know how easy to do Prestack migration, right? The principle is simple. But because you do the sample by sample for a whole data cube, that really time consuming. But all the time, the total amount of time is linearly proportional to the number of samples, right? Apart from the time writing or reading your data from the disk or writing back to the disk, right? But for the computational part, it's straightforward, linear to the number of samples. from the data. The migration methods, for the post-stack migration methods, we mentioned we have two types of methods. One is the integral method, another one is a very equation-based method, right? For the pre-stack, we have the same. One is the integral method, one is a very equation-based method. For the post-stack migration, we have two types of integral method. One is called Kirchhoff migration. Another one called deflection stack. If we remember that, right? Kirchhoff migration is you spread a data sample to the model space, follow the curve. But deflection stack, just like an NMO stack, you try to imaging one point in the model space. You go back to the data space to sum all the energy follow a diffraction curve. You sum the energy together and take the energy put into the imaging space, right? So in terms of implementation mechanism, one is based on the data space, another one is staying in the model space. That's the difference, right? Okay, now for 3D, for the pre-stack migration, we cannot using diffraction stack. We cannot use diffraction stack, right? That's the only difference. We cannot stay in the model space and go back to the data space to sum the energy follow a diffraction curve, right? Because for pre-stack, we consider all the complicated elements. For example, the dipping, right? For example, the azimuthal, so it's not straightforward diffraction. That's why. Apart from that, everything else just Imperial. We have a integral method. We also have a equation method. Here we based on the we have a last time we introduced 4 methods. One is called the final difference. One is called the explicitly. Okay, another FK, and something else. Okay, so final difference basically is in the TX domain, time space domain, right? And if you make some assumption, you can transfer your time steps to the frequency. So you end up something called a FX migration method. This one very often use explicit method, right? Explicit method. And then if we make a further assumption for each individual layer, the horizontal velocity is constant. You can do the second Fourier transform to transform X to the K, right? So you end up with data in the FK domain that's even faster in terms of migration because everything in the FK domain, right? That's a typical FK method is called a phase shift method, right? Phase shift method. Phase shift method basically is for, we call this something else, right? Phase shift method means your time and space both in the both direction. You assume the velocity are constant in the both direction, right? In terms of the migration capability for the final difference, if you recall that, I think ideally we can migrate subsurface reflector up to the 15 degree, right? And the explicit method we can do up to the 45 degree because we include the 4th order into the calculation. And the FK we can do up to the 90 degree, right? So this is the what we learned for the Prestack and the Prestack, same thing here. But the implementation will be, details of the implementation will be slightly different, but principle same. So let's talk about migration method. First one, the Prestack kickoff migration. Kickoff migration is same principle as a Prestack migration, right? We call it zero offset migration. Same principle. And the implementation steps are same. You do need to do ray tracing. You find the physical ray path. Sorry, not physical. I mean the ray path. Ray path means the strong energy package travel around the subsurface, right? Physically really means that the wavefront, actually the ray path is not perpendicular to wavefront. Ray path means the strong energy propagation path. If you let's say you learn more about the wave phenomena, you will know the difference. Okay, and after the calculation for travel time, you just do the summation or integration of energy flow that ray path away from for the travel time. Okay, so there's two elements. For ray tracing, you can have simply use like a geometric use. You can have start from short point, and then the ray path is spread away. Or you can say, okay, I have source point, receive point. In between, the ray path must follow the minimal travel time path, right? That's called geometrical one. But also, this one here, Occidental equation. What is this? This means you use the wave equation, but you assume the wave frequency is unlimited, extremely infinity high frequency, right? That's the theory. Okay, so that means the travel time or ray path follows the differential equation. That's right. But this is one of the methods. If you know the final difference for the wave equation, so you do know this straightforward. And for the migration, you can do sample by sample. As we showed the theory, we use orbit concept sample. But also we call the imaging response. We do the one trace by one trace, right? For single trace, we do the whole imaging. And then do a second trace and so on and so forth. Finally, all the images, we sum them together to generate the final migration image. That's the implementations, right? Straightforward. And this one also can be targeted. That means we calculate the trace by trace, but we only, in the model space, we only focus the small portion of model which we want to focus on, right? Which we want to analysis. That's that one, okay? So that means if anything far away from this targeted portion, you can simply ignore that. That means you save a lot of time. Okay? Also, you can redo that migration for that small portion if you have done that, and you suspect the image is not right, and then you can redo that part, right? So you can always go back to the local migration. This is important I mention that because when we talk about different methods later, some methods we cannot do that. If we want to redo migration, you need to do the whole. You cannot do the piece by piece. But for the catchment migration, you do have such a flexibility. That's why this method is quite routinely used in the industry. Even nowadays, you have a most advanced method, but you still use this at least as a initial step. Okay. So you do not straightforwardly go to the so-called sophisticated migration method. Right, that was picture of migration. For the web equation-based migration, let me repeat. For web equation-based method, we have 3 elements, right? 3 elements. So one of the final elements was imaging. Okay. Then before the imaging, we do need a way to solve the individual equation. But why do we need to solve the individual equation? Because the first element, downward continuation is based on the differential formula of a first order wave field derivative, right? So in the first order derivative, we do need to calculate the first order derivative. So that means we need to solve equation, right? And then with the imaging condition, okay? So that's the 3 elements. But here, for the Prestack migration, we also have 3 elements, but the imaging condition will be different. That's the difference, okay? So we need to understand in terms of physics why the imaging condition is different, and then we can assess the final imaging. Okay? Right. So the Prestack migration, finally, I'll give you let's say the bad news first. Prestack migration, the final result is not true subsurface imaging. Why is that? Because we will do correlation. The imaging condition here will be the correlation. That is not true subsurface imaging. Nobody really mentioned that because when people write a paper, they say, okay, I have wonderful methodology. Maybe this can cover everything around the world. That's not true. But as a student, as a researcher, we should be, somehow in a critical, take a critical view. I tell you the truth. Prestack migration result is not a true amplitude. Let's say that way. Okay, so that's why I emphasize that, because the image condition is different. Now let's the equation here we used based on the double square root. The procedure also based on the downward continuation, right? And for the migration, we can apply to short gathers or receiver gathers or common offset sections. Doesn't matter because we do trace by trace, right? And then finally, we just stack all the images together to generate final image. Okay. When you solve this wave field, you use the wave equation. So that's the where wave equation is, right? Wave equation is only one element in the migration. Although it takes much longer time to calculate, right? But it's only one of the 3 elements. Emphasize here in red, this is a global method. If something wrong, if you do not happy with that, or if you want to change some parameters, you need to redo from very beginning. You cannot do it in a sort of local area-based or target-based, right? That's the difference. That's why this method takes much longer time, because if we do a global method, it means you require all the data to be considered. This is the Prestack wave equation methods. So the key equation here is a double square root. Double square root. That means double square root means one square root describes the wave propagating downgoing to the reflector. Another way is upgoing back to the receiver, from the reflector back to the surface. So that's a double square root, right? And you can use still use a downward continuation, either for short or receiver, both going down simultaneously. As we said in the Prestack migration, this is a typical depth migration method. You do the step by step in terms in depth. So that is that. And the source receiver, you can treat them separately, right? So one is used to use the source part, you downward continuate the wave field, and the receive part you also do downward continuation. So best, and then finally, because you have two wave fields, one's from source side, one's from receive side. So how to match, how to generate volume imaging? Because it's assume for the reflection, for the reflect point, the source wave field and the receive wave field, the two wave fields should be identical, right? That's the idea. Should be same. So what do you do? How to measure the two wave fields are same or not? You measure similarity based on the cross correlation, right? It's natural. So the image condition will be the cross correlation of a two wave field, one from the source, one from receiver, right? Cross correlation, if we do the normalization, cross correlation give you what? Give the coefficient, right? Between 1 to -1. If it's identical, the cross correlation will be 1. If not, or if opposite, -1. So the imaging of Prestack migration is, in fact, is cross correlation. It's not exactly subsurface reflection. You understand this point? Right? It's not subsurface reflection. In the Prestack migration, the image condition, we say, okay, we assume the subsurface interface is a so-called exploding interface. We assume the source point is at the reflector. Right? You gradually from far and gradually when you move down to the source point, so you know exactly the reflector, right? So that point is a reflection coefficient in the Prestack. But in this case, because you do the cross correlation of two wave fields, the cross correlation is not exactly the reflection coefficient. Okay, if we read the papers, nobody mentioned that, but in fact you know that. You should know that. Okay. Nevertheless, Prestack migration will give us the good resolution and the good structure, right? So if we want to do the further development in this field, you can somehow come out so-called true amplitude migration. That's the research direction, right? At the end of this lecture, I will tell you a number of research directions. This is the one. Get the true reflection coefficient imaging from Prestack migration. That's the number one now, right? Okay. So here said, should give us same wave field at each reflection point. This is the assumption. Based on this assumption, we do the imaging, which means cross correlation. I already said that. The image condition is you do the source receiver both at X at the time Z. Cross correlation, because your wave field is in the time domain, right? Yeah, in the time domain. So cross correlation of a two time series, you basically it's another time series, right? So in the Saussure imaging, we just take the zero leg. So t equals 0 here is nothing. There's no any physical meaning, just a zero leg. It's nothing to do with your data, nothing to do with your subsurface model. That's a zero leg, okay? It's different from Prestack migration. Prestack migration t equal to 0 does have physical meaning, but here just a 0 leg. Okay. So calculate the correlation at time 0. That's what we do. Let's show you an example here. On the left-hand side here, this is one shot gather. One shot gather. Here is basically direct wave. The source point here, and the receivers follow this red dots line, right? And then this one we call the snapshot. So you can see the wave start from the source point and gradually spread out, right? When they hit an interface, they will have a reflection back, right? So seems quite complicated. Okay, but also you can see this salt body here. Salt body has a strong velocity, high velocity, and high density. So you can see this part, there's no much wavefront inside the salt body. Why I emphasize this short gather here, often we see, this is for 2D model, right? Only 2D. We do see this one, this is a reflection, but we see something look like this here. You know, this hyperbolic curves has an apex not at a 0 offset, but it's non-zero, right? So just what we said, we do need a Prestack migration. We do have one flat one here, flat interface, source, underneath the source you have flat interface, right? But we also have the side dipping event, you see that? One of PPT I showed, right? So it's the subsurface structure is not that simple single structure, but you have at the same time or same depths, you have two, at least you have two or even more. Right? In this case, you have reflection here, but you also have a side reflection from here. You can see that. Because this one from side, the travel time longer from here, right? So the time delayed, and the peaker actually is here, right? So that means that one, when the reflection point is on the top of this salt body, you have a shortest travel time, which is here, but it's slightly on the left. Although your source receive offset is smaller, but your travel time actually longer because the velocity here is lower than inside the solar body. You see that? Also, from here to here, your central point is here, right? So offset is smaller, but the travel time even longer. This travel time, you can source here, receive here. So you can this the phenomenon here. That's why we emphasize we do need to do Prestack migration. Okay, NMO Prestack migration just give you a rough idea, but for the subsurface image, you do need a Prestack migration. That's one thing. Okay, now I said when you have a source here, you just you know the source wavelet, right? You do the forward modeling. You have a wavefront here for any time, any single time. You do the cross correlation with another wave field, which is from a receiver. From receiver. So receiver means this is your recorder seismic data, which means here. This is the recorder seismic data. You treat this whole seismic data whole data as a single source, right? And then you were propagating backwards from here, also downward continuation, right? Downward continuation. Start from here, gradually move down. And what do? You do the cross correlation between these two, right? Cross correlation between the two at each individual depth. Okay. And then finally, you take a 0 leg, t equal to 0. Okay, maybe you slightly confused. Look, let's say this point here, even this point, put this point, actually this is not a single sample here, right? This at a different time, you have a different sample value, right? So even for this point, you have a time series. You can see that. In the source wave field, you also have for this point, you also have a time series, right? So what do? You use this time series at this point. You record the time series, and another time series from a source wave field. You do the cross correlation between the two time series, right? And then you take zero leg. You find out the cross correlation, and this final cross correlation at the time zero give you so-called migration result. So you have X space, you have X, you have T. Sorry, X and Z. Okay. It's not so straightforward, but you think about this is now if we, for any moment, this is a one XY profile, right? But if for next time you have another profile, basically here I displayed is a 3D cube. Even this model is 2D, that's a 3D cube. In the source wave field also you have another 3D cube, right? So the 3D cube we have a 3 axes, one's X, one's Z, another time, right? That's 3D cube. So for individual XZ points, you have a source time series and the receiver wave field time series, and that too you do the cross correlation and take the zero leg as the final result. That's migration. So final result after the point after point to point cross correlation and take a zero leg sample, you end up this result, right? Well, here this is just one of the methods to calculate the wave equation, to the wave calculation. That's not really the migration mechanism. Really, the migration mechanism is downward convergence to both sides, and finally cross correlation in between. This is one how to solve the equation. That is the final result. Okay, let's have a break, and then we go to the depth migration.